Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it is my pleasure to introduce Romit, who's an assistant professor at Duke. He did his PhD from UIUC and in 2006, and within 1.5 years, he's already gotten the Career Award and is doing really well. He received a lot of press for this work that he'll be talking about today, like newspapers in India calling him like the next generation great scientist. So Romit, I'll let you describe your work.
Well, that was an exaggeration, but yeah. My father called me up and said, Indian American scientist? What does it mean? So I was like, okay. Okay, so let me get started. I have 75 slides, so I don't want to be too long. But again, don't worry, most of my slides are one-liners and two-liners. Okay, so the topic for today is designing a virtual information telescope using mobile phones and social participation. And before I actually jump into the technical stuff, let me talk a little bit about ourselves. We are the Systems and Networking Research Group at Duke, and we are 5 PhD students, 3 undergrads, including one who's interning over here and one of the PhD students over here. We mostly work in the several layers of the protocol stack. Instead of going into the details, if you abstract it out, what we are really doing has essentially 2 threads. One is we are looking at physical layer capabilities and exploiting them at the MAC layer and higher layer towards better protocol design. And the other approach is we are looking at applications and services at the highest layer, the application layer, and figuring out what are the challenges that need to be resolved in order to actually support these kinds of applications. So again, if we abstract what we are doing, two themes, one from the higher levels, what are the visions, what are the top-down research problems, and one from the lower level, what are the physical layer capabilities that can be exploited at the protocol design on the higher layers. Okay? So that's essentially the theme of our research, and we have 4 ongoing projects right now. And one of them is called Shuffle, and let me just give you a one-line description of each of them. Shuffle is basically looking at interference cancellation and message-in-message capabilities, in which the basic punchline is interference is not all that bad a thing. If you understand interference, you can actually cancel it and do lots of interesting stuff with it. So it's like keep your enemies close to your heart in some sense. Try to understand the interference and thereby cope better with it. And we have been designing protocols with those capabilities. Spotlight is about using beamforming antennas in wireless mesh networks, and we are designing hybrid TDMA, CSMA kind of protocols in that space. SmartCast is about link layer multicast for video and audio kind of applications, again with beamforming antennas. And today's talk is about information telescope, which is essentially building a mobile social participatory network using mobile phones. So this is essentially the organization of the talk. I'll start off with a little bit about the bigger vision, the systems and applications, some of the research challenges, and some of the ongoing work. Okay, so let's get started. To set up the context, we believe that next generation mobile phones will have a large number of embedded sensors in them. There are already cameras, microphones, accelerometers, GPS, etc. Next generation there might be compasses, health monitors, pollen monitors, air quality monitors, water quality monitors, a whole bunch of them. And our view is each phone may be viewed as a virtual micro lens, and this micro lens essentially exposes a micro view of the world to the internet, right? And now with 3 billion active phones in the world today, right, and it's actually growing faster, by end of 2009 it's supposed to surpass laptop sales. So with 3 billion active phones, our vision is really metaphorically captured in this diagram, where all these phones are actually working as a micro lens, and we want to design a software virtual information telescope which will allow you to look at the entire world through the eyes and ears of the phone, through the internet, right? So the users of this telescope should be able to zoom into any part of the world and look at that part of the world in real time through the sensors in the phone. And those sensors need not necessarily be cameras only. It can be, is there Wi-Fi at this location? What is the light, sound, temperature at this location, etc. It can be the entire spectrum of signals, right? Now, several applications can come up, including disaster recovery, healthcare, education, etc. But perhaps more fundamentally, this might change how we browse, query, learn, process information from across the space, right? Now, that's a kind of a broad vision, kind of a metaphor, if you will. One instance of this vision is what we do in the project Microblog, and it has essentially 3 steps, which is content sharing, content querying, and content floating, right? And let me quickly go through these steps, again through pictures, and hopefully it should be clear. So content sharing, the key idea is, instead of having people blog on their laptops and desktops, right, we are encouraging people to blog on their mobile phones. And so a person goes to a California beach, takes a video, talks about the beach, likes the beach, and presses the send button on the phone. The phone client, the microblog client, takes all this multimedia information, timestamps it, location stamps it, and sends it to our server, which then positions that blog at the right place on the map, on say Google Maps right now, right? And as a user of the internet, say a virtual telescope, the user goes to Google Maps, for example, zooms in into California beach and sees what people are saying, maybe videos, audios, etc., etc. Right? Well, this is, when we started with this, it was kind of new and exciting, but I think now we've seen a whole bunch of applications which are very similar to this, right? So what we thought is, if we want to make this a little bit more novel, what we said, hey, you can actually add querying to it. So the idea is, this user is trying to plan his vacation, say, to California beach, and sees quite a few cool videos about what are the cool places to go to, but no one talks about, say, parking in around California beach. So what Microblog allows you to do is, you can go to Google Maps, select a region using your mouse, and then record a query saying, hey, I'm Romit from Duke, can someone tell me if there's good parking in this region? And then send the query from the interface, which will actually geocast that query to all phones in that region that was demarcated by the user, right? So so people who are around the beach at that point in time will have these queries pop up on their phones, and let's assume for now there are some incentives to reply. Someone among them might take a picture of the parking lot, might say, well, $5 for the day, here you go. And that's another microblog that comes back and gets positioned on the map as well. So if you generalize it a little bit, it's like strangers of the world asking questions to each other on a spatial domain, and that might be interesting. Okay, so we said, okay, good, but we might be actually able to take it even one step further, and the idea is, okay, by the way, before I forget, now these kind of queries can be participatory, in which the user actually takes a picture or says something, or it can be automatic, where, for example, you say, is there Wi-Fi at San Diego beach, right? And the phone can actually resolve the query for you and say, here, there are 5 free Wi-Fis, so on, and then send back the query, reply, and you can get information. So queries need not be only participatory, they can be automatic also, much like the typical notion of sensor networks. Okay, so we tried to extend this to the next step, and we said, okay, till now what we've said is essentially taking information and superimposing on virtual space, in this case Google Maps. Right? We could also take electronic information and superimpose on physical space. For example, I go to a restaurant, I like the food, I make a microblog about the food and float it at the restaurant itself, and I push off. Someone else comes to the restaurant, and that information automatically gets downloaded onto the phone, and he says, oh, Romit had Kung Pao chicken at this restaurant, looks good, he recommends it, maybe I should order it. So it's as if you're floating post-its in the air, you're writing post-its and floating it in the air and moving away, and someone else who is going by that location reads the post-it and might even revise it, add more to that post-it. So, and that's why we call it post-its in the air, you're essentially floating information on physical space. Well, yes, the implementation, as you can imagine, is essentially there's some server which knows where you are and accordingly pushes information based on your phone's location. Good. So please do tell me if something is not clear, or if feel free to interrupt me. I'd love to actually have interactions during the talk as opposed to questions at the end. Okay. So we believe that if you design this carefully, there's a whole bunch of applications that can be enabled, and we've been thinking about a few. One of them is tourism, clearly. You can plan your tour based on other people's feedback. Micro reporters, where everyone can be a journalist, and actually CNN already does this, I report. Another application we've been kind of excited about is on-the-fly ride sharing, where the idea is, hey, how about if I get out of my office and I want to go home, I pull out my phone and I kind of see all people around me in my, say, 2-mile radius who can give me a ride towards my home. Right? And if I can do this electronically, maybe it's like an eBay, a real-time eBay for ride sharing, and in the face of current gas prices, people might appreciate that. Now the fourth one, which we are also thinking about, is essentially pitched for the developing regions, or maybe rural regions, and we call this virtual order on physical disorder. And the basic idea is again similar. So a lot of people who go to India, there's not as much structure in India as like in US. For example, roads are not labeled, you don't know where to go, where to go for taxi, what to do, etc. And for an American who goes to India, they don't even speak the same language, right? So maybe one idea would be to take information and superimpose on physical space so that you get off the flight, your phone tells you walk straight, take the door on your right, that's the taxi stand. Right? And as you keep doing what the phone tells you, your phone recognizes that you're in this location and tells you what to do next. So if you really push it to the extreme, traffic lights should be on your car. There should not be any infrastructure. Your car dashboard should tell you, well, it's green or it's red, and you should go accordingly. But yeah, that's extreme. People get psyched out when I say that. Okay, so a whole bunch of applications, and we actually prototyped a microblog with Nokia N95 phones, and there's a server, and I can skip a little bit of that in the interest of time. And actually the beta version is live at this point at synergy.ee.duke.edu, and you can actually get a link to that from my web page. But to give you a quick idea of what it looks like, so we were demoing this in Census last year, and we were in Australia, Sydney, and there were phones in this region, and so we drew this box, and we typed a query which says, are there restaurants close to the Opera House within walking distance? And my students had these phones, and they were walking around in this Opera House region, and the query actually showed up on the phone, and one of them typed out, yep, there are plenty of restaurants, and when they typed that out, that reply came back, and I said, okay, now I can go. Right? Well, this was an orchestrated demo, but you can potentially you can imagine what it should look like in real life. Okay, so then we thought, okay, good, we have the demo set up, why not give it to some of the Duke students and see what they feel about it. So we did a survey kind of a stuff with 12 volunteers, 4 phones. We had only 4 phones then, so we gave them out in 3 rounds. The GUI was not great and people complained, etc. But still, from the exit interview, I think we had a few very interesting comments which we were not quite expecting. So here are a couple of excerpts from the exit interview, and most of them said, hey, this is fun, but we need a cooler GUI, right? And we absolutely recognize that. People also said that we had to carry 2 phones and we often forgot, etc. So those kinds of problems were underlying this kind of a survey. But more interestingly, people said, of course, privacy control is vital. I don't want to give away all my pictures to others or all my videos. But people said unanimously, we don't care about incentives. And when asked why, people said, hey, it's very interesting to reply to people, especially if we know who is asking. It's kind of a service that they're doing to others. Again, this is the undergrad crowd, which might be a biased crowd, but they felt it's cool to reply, and they're kind of helping other people getting replies to questions that they might have. The third one is people said voice is personal, text is impersonal. They did not want to record their microblog, and then if they did not like it, they didn't want to delete it and all that. They said, hey, it's easier to write text and correct it the way you want it. And the last one was logs mostly turned out to be 5 p.m. to 9 p.m. And well, that was the time when they were really off from their regular schedule. And that probably says something when it comes to battery usage of the phone, etc. Okay, so far so good. We believe that microblog is a rich space for developing applications and services. But the question that most of you might already be thinking in your minds, so where exactly is the research here? Yeah, that's the question we also actually struggled for some time. But then I think we hit into a whole bunch of stuff that we are really convinced are very important research problems. Especially when we were demoing it, things were pretty good. Well, yeah, not much research. But as we started dishing them out for people to use, lots of things started coming up that we didn't see in the demo phase. So I'm going to essentially focus on these three research challenges. One is energy efficient localization, one is symbolic localization, and the other is location privacy. There are several others, but I believe we do not have the skill set to actually address them well. So right now they are low in our priority. Okay? So please feel free to ask questions at any point in time. A quick disclaimer, most of this work is ongoing, so it won't be mature, but I think the talk is more about identifying the problems, understanding the problem space, and essentially getting a feel of the solution sketch as opposed to full-fledged mature research solutions. Good. So problem one is energy efficient localization, and we call this project NLOC. Okay. So we gave out these phones to undergrads, and they came back within 10 hours and said, hey, the battery is dead. And we said, why? And we figured out through extensive measurements that GPS is extremely energy hungry. And with the latest Nokia firmware upgrades, it comes to around 8.5 hours without any other application running. When you run other applications, it's even less. The screen was off too, except maybe a couple of times it turned on for some weird reason. Maybe our application was doing something. But yes, the screen was off too. Yeah. So, and we did all these measurements, and the GPS we saw it consumes 400 milliwatt. We did AGPS as well, which is assisted GPS. That was marginally better, but nothing, something like half an hour better. And then the idle power was really 55 milliwatt, which is really the green line over here. The red line is the GPS floor, and the orange is Wi-Fi.
Does it vary across GPSs, or is this more or less
So we've tried across two phones, and
the same Nokia?
yeah, we don't know what it's across different platforms. But we've heard complaints from other people also about.
It's bad, because I was wondering if, based on the GPS chip that you're using, whether this changes drastically.
I don't know. Okay. So then people said, hey, of course, there are a lot of other alternate localization mechanisms. PlaceLab from Intel, Skyhook, they're all doing Wi-Fi or GSM-based localization. Yes, it saves energy. Wi-Fi gives you around 20 hours. GSM gives you around 40 hours. That's great. But hey, there's a cost to that. And that was that with Wi-Fi, even in dense regions, you get around 40 meters of localization accuracy. With GSM, it's 400 meters. If you turn on iPhone, they give you a big circle of where you are.
This is outdoors.
What is that?
This is outdoors.
This is outdoors. In indoors, GPS is not working, so if you come to my office, you'll see phones lined up on my window, all trying to get a line of sight to the satellites. Maybe some application. Jit.
Why is it 40 meters enough for locating restaurants?
Not enough?
Well, it should be enough for locating restaurants and stuff like that, right?
But there might be several applications which might want to know where you are, say location-specific advertisements. 40 meters is not enough because you might be one of 5 stores in a mall and you don't know which store you are in. You don't want to advertise toothpaste to a coffee drinker, in some sense. Yeah. So I'll come to that in a little bit. Right? So again, there might be a class for which it's fine, but we believe there's also a class for which 40 meters may not be fine. And by the way, this is for dense urban kind of areas where there is pretty good amount of Wi-Fi density. So the trade-off summary is something like this: 10 hours, 10 meters, 20 hours, 40 meters, 40 hours, 400 meters. And the research question we started to bump into is, can we achieve the best of both worlds? And 10 meters of accuracy may be 40 hours of battery lifetime. So the basic intuition that we are trying to use over here is that, hey, human mobility is not Brownian. People don't like go from here to there in seconds. And there are a lot of patterns in people's behavior, in group behavior. There's a lot of persistence that you can actually exploit to predict mobility. And if you can predict, then you need not do energy localization sampling, right? And that's the basic idea. But well, that's still kind of loose. Let's actually try to formulate this a little bit better. So what we say is, okay, we are given a trace of a human mobility. We are trying to convert that into an error versus time graph. And this graph is like follows. Suppose this is your LT0 is your location at time t0. And suppose you're over here and you start moving, and say you pause over here for 3 time units, and then again you start moving and you pause for 2 time units. And suppose you know the location, the original location from where you start. You can convert that into this graph, which says your original error is 0, and it keeps increasing till t2, this one. And then you have paused there for 2 time units, it's stationary, again it increases, it pauses. So that's a pretty quick translation of this trace into the error time graph, right? And now we said, okay, suppose you took a GPS reading at time t4, then essentially your error drops instantaneously to 0, and then again when you start moving, your error starts going up. I've simplified this a little bit. People might be coming back to their original position, and this thing might decrease, and all kinds of things have happened. But without loss of generalization, this should give you the idea that we are trying to get. So if you do a GPS reading over here, you've expended some energy, but you've gained accuracy, and that's the shaded region, right? If you do, say, another Wi-Fi reading at T6, you've again expended energy, but you've gained accuracy by that amount. Essentially, your total error is the area under this curve, right? And as you take more and more readings, you're kind of pushing that envelope downwards so that the area under the curve starts reducing, right? And now the question is, given an energy budget E, a trace T, and a location reading cost, say what is the cost of GPS, cost of Wi-Fi, cost of GSM, right? Can you come up with a schedule which will actually optimize your localization error for a given energy budget? So where else should you be cutting this graph down so that your overall or your aggregate area under the curve is minimum, right? And that seemed like to us like a well formulated problem, and we have a dynamic program solution to that, with which we can actually find out what exactly is the optimal that you can achieve for a given trace and given energy budget. I'm not going to go into that, but I can talk about that offline. But what it gave us was the offline optimal offers the lower bound on error for a given energy budget. But we need online algorithms to actually do it while mobile phones are moving. The online optimal is difficult, so we need to design heuristics. Okay? So we started looking at heuristics, and we've not gotten too far, but we have some ideas. And again, the main idea is you do prediction based on human mobility. You also do prediction based on how the accelerometer of the phone is changing. If you are static and you started moving, your accelerometer can give you hints. If you take a right or a left turn, your accelerometer can tell you stuff. So you use all that information to actually do prediction. Okay? By the way, the predictive heuristics can actually be fed into the optimizer, essentially because if you do better prediction, this black curve would start coming down because your error rate would start decreasing. Right? So we fed predictors into the system, and we have essentially 3 predictors right now. They're all very simple. One is you do simple interpolation. So essentially you say, well, I'm going to take one GPS reading and then a couple of Wi-Fi readings, and I'm going to essentially extrapolate my GPS readings in the direction of Wi-Fi. So I take a GPS reading at time t0 and I take a Wi-Fi reading at time t2, say. I extrapolate my location or my movement pattern towards location at time t2, but using my previous GPS reading. and that is better than just saying, okay, my current location is LWT2. Right? Again, simple, but well, let's see. I mean, it might work, it may not. The second thing we are doing is saying, hey, how about recording user's mobility profile, and at any given time, if your current mobility is similar to your historical mobility pattern, maybe you use your historical patterns more often. Right? Yes, that gives you something. And then we are using accelerometers. We are saying, okay, at this traffic intersection, your accelerometer says with 0.78 confidence that you've taken a right turn, maybe I should believe that. And we are actually getting good results out of the accelerometer about taking turns.
Usually have their mobile phones on them at all times, and there are significant differences in mobility when you're driving in car versus when you're walking in the mall. How do you separate those periods out? Because you can't take a view of history that's combined across the two.
Yes, absolutely. So again, each of these historical patterns, you cannot rely completely upon them. They all give you hints, and you take all these hints and you try to predict. And the other thing is, if you see that there is good temporal correlation in your history, morning 8:30 to 9, for me it's 9:45 to 10:15, you drive to your office. If you can use some of the temporal correlation, you can actually benefit. But yes, right now we have not used that in one of the heuristics or any of the heuristics we've done. So, but accelerometer, we are getting good data because you can predict whether you've taken a right turn or a left turn. Yes. Okay. Now, the third thing that we are doing, oops, my PowerPoint is stuck. What is that? Oh, I don't know. Okay. Oh, okay. Thanks. Okay. And the third thing we are quickly doing is, okay, we are saying, hey, if a person has gone to a new place, we don't know what he's going to do, so why not use population statistics from there? So if you have an intersection and you know 90% of the people take a right turn, maybe you can use that information towards your prediction. And we are trying to gather that kind of a distribution for every intersection in the Duke campus, and we've used some tricks that I can talk about offline. And so this is very early results, came in yesterday night from my student. And this is the optimal, this is a heuristic which essentially takes a k random set from the optimal sequence. By the way, the optimal sequence is like, at time t1, take GPS, time t2, take Wi-Fi, at time t3, take GPS, time t4, take GSM. So it's a schedule that you should take to minimize your accuracy, to maximize your accuracy for a given energy budget. And then this random case, you take a subsequence, a part of that sequence, and you repeat that for your localization. And this is, if you have the energy budget, you divide it among GPS readings, and you keep using that GPS readings, and it turns out that actually GPS is pretty bad, your optimal can be much better. And my belief is we can actually, well, by the way, this is the best case. In the other graphs that we have, this is actually higher, and we believe that you can actually use all these accelerometer stuff to do better prediction. Okay, so thoughts, localization cannot be taken for granted. I think the energy perspective is important, and it would be a critical trade-off for all kinds of applications for the future. I think there's substantial room for saving energy, especially sustaining reasonably while sustaining good accuracy. However, after we've done this to some extent, my feeling was physical localization may not be the way to go. In other words, an application may not care what exactly is your coordinate. People might care what exactly is your context, and that's why we are trying to look at symbolic localization, where the idea is your location is essentially your context, and the application cares about that. Okay, so let me motivate what the problem is in a little bit more. So services may not care about physical location. The service might want to know, for example, if it's a location-specific advertisement, the service might want to know if it's a coffee shop, if it's Walmart, if it's a movie theater, if it's a parking lot, etc. Right? Now, one way to do this is, hey, why don't you take your physical location and reverse map it to find out what is the context, right? So you take the location of the phone, You look up a database and you say, this location is in Starbucks, and therefore you know the context, right? But then unless your physical location is remarkably precise, you'll never be able to say whether this phone is on this side of the wall or that side of the wall, and your context might change dramatically. And that's where I was saying a person in Starbucks does not want a coupon for grocery, right? What is that?
Send him both. Send him the Walmart coupon and the Starbucks.
Well, you don't want to do spam there also. You want to restrict it as much as possible, especially with energy, interest matching, and all kinds of stuff. Right. So my belief is with physical infrastructure-based localization, sub-meter accuracy is difficult. Maybe we should do something completely different, and that is what we call symbolic localization. And the idea over here is, why don't you sense the ambience around you and try to say where you are? And that leads to this project that we call Surround Sense, where the basic idea is the phone's microphone listens to all kinds of noises around you, sounds around you, lights around you, and forms a soft signature of what this place is. You train your system with these signatures or these fingerprints, and then you localize accordingly. Right? So you gather fingerprints from mobile phones, you might use microblog for that, and then you match a phone's fingerprint to your trained database. Right? So the basic idea is your GSM localization says you're in the mall, say 400 meters accuracy or 300 meters accuracy, and your surround sense augments that by saying you're in the Apple store or you're in Best Buy, just by understanding the fingerprint of that particular store. Okay. So before we didn't believe that this is going to work, so we said, hey, 2 mobile phones, we don't want to invest that into surround sound right away. Let's start off with very crude sensors in T-mode invents, and we use the light and sound sensor on these modes. And we got good results, so we are currently prototyping it on Nokia N95s. So what we did was we took the sound signals and we transformed that into the frequency domain through a Fourier transform, and then we looked at different frequency bands. Very interestingly, we saw that there are very good signatures, like if a microwave is on, certain bands are high. If people are talking, certain bands are high. Vacuum cleaners have signatures, refrigerators have signatures, and the idea is, if you know, hey, the vacuum cleaner is on, the microwave is on, the light is dim, maybe this is a Starbucks or a restaurant or something like that. Yes?
Are these sound sensors comparable to the mics that are on?
No, these are way more cheaper. Okay. So our belief is once we go to the phone platform, we can do much better in terms of this fingerprinting. Yes. But even at these lower frequencies, this is from 20 hertz to 230 hertz, so it's very low frequencies. We do not catch the high frequency ones. Yes. But we've extracted 48 features from the light and sound, where most of the features are different frequency bands, and then we do a 48-dimensional fingerprint, and then we do basic, very simple data mining classification algorithms. Yes.
Does it matter if the phone is in my hand versus the phone is in my pocket?
So right now, we do not know that. But right now with our sensors, we've actually turned it in all kinds of orientation, including the other way, and it did not matter much with the sound. With the light, it does. But light, we are not depending on it too much anyway, simply because your phone is going to be mostly in your pockets, and I don't think the camera would actually pick up light too much, but sound itself is doing pretty good. So let me get to the results a little bit. Okay, so this is essentially the block diagram. We take raw audio data, divide into blocks, do FFT, extract features, similar for sound. We have a fingerprint with 48 features. We do a nearest neighbor algorithm, basic data mining nearest neighbor algorithm, and we get what is the location of the phone. Right? Again, remember, you cannot say the globally unique location. We assume that GSM tells you you're in the mall. We are essentially discriminating between shops in the mall. We are not saying you're in Durham Starbucks versus Seattle Starbucks. We cannot do that. Right? Okay, so here are results, and these are a whole bunch of restaurants and coffee shops, and this is Street, and this is Whole Foods. This is Twiney's, which is Duke Cafe, which sucks. Blue Express, which is actually a good cafe. No, it might be the other way actually. I'm on record, so yeah. So we actually did autocorrelation and cross-correlation, and you'll see that for Dales, so all of them, you're able to localize it very well with sound and light together. We were having some problems with streets. We are not able to say, although, so this data shows we were able to, but later we got a whole bunch of other data in which the street autocorrelation is not turning out too well. And I'll tell you what the intuition is just in the next slide. But the point is, when we used both sensors, light and sound, it turned out better than just using sound, which was much better than just using light, because sound proved to be a very good fingerprint of the place. Okay, so why this really worked, and we didn't expect it to work, but why it worked was, when you look at a whole cluster of stores or shops in an area, they are designed to be different. You don't want to have 5 Chinese restaurants one beside the other with the same ambience, with the same lighting, same sound, same music playing, etc. Economic reasons want you to design them differently so that the business gets distributed, so on and so forth. So there's diversity in spatially clustered business locations, and we are trying to exploit that diversity over here. If they were very similar, it would be hard. Right? Okay. Streets, unfortunately, does not have that property. So most of the streets seemed to be similar in terms of light and sound with cars passing by, and we are actually having a tough time classifying streets, one street from the other. Question?
To train this database, how would you expect people to actually...
So I spent around $500 paying for my students' dinners and cafes right now, because they go and train these, they go around these coffee shops in these locations getting fingerprints. But my assumption is, my hope is that when we use microblog, if people are blogging, maybe we can extract some of the ambient data from there and keep training the database. Right? And maybe if you get location over there, you might be able to do good. So yeah, maybe we can use microblog peer-to-peer something to actually train it. But for now, we've trained it just to figure out whether this at all works or not. And we are in that stage right now.
A little bit of a circular dependency, right? Because for microblog location to work properly, you need a location system. And you need microblogs for the location system to work.
Right. So essentially what I meant over there was, suppose someone goes to Starbucks and blogs and says, I am in Starbucks. You can use that to say what
you have to actually extract that from the microblogs.
You parse the data, parse the content in some manner. But I'm assuming this can be done with this training of it. Okay. And maybe if a phone has a lot of battery, right, maybe the phone can use the GPS and tell me what exactly is the location. It would work, yes, that's probably true. Okay. So then we said, okay, we can actually augment symbolic localization with accelerometer. So if you can't say where this guy is through light and sound, maybe you can look at the accelerometer reading, and if the guy is actually, the accelerometer reading says the guy is walking up and down, maybe it's a Walmart, this guy walking up and down aisles. If this guy has been sitting and the lights are dim and the noise is low, maybe it's a restaurant. So we added accelerometer on top of this, and I'm not going to talk too much about this, but the idea is people's activity can be guessed through accelerometer readings, and if you can correlate that to the context, maybe that also gives you localization information. So again, very similar approach over there. You train the database with the accelerometer. Let me jump quickly through this. Again, this is a k nearest neighbor classification algorithm. What we've done to save energy a little bit is the phone extracts the feature from the accelerometer and only sends the 3 features to the server, which then runs the matching algorithm with the database and essentially feeds it to the classifier. And that's because you did not want the phone to actually export all the accelerometer data to the server. And this is something we have built in the phone right now, and we have the demo, and this is in a Mobicom workshop paper this year about GPS-free localization. And we call this project AMPLE, which is Accelerometer Augmented Mobile Phone Localization. Good. So here are again some stores, restaurants, fast food, and different kind of stores, and we see that there are sufficient diversity in them to be actually able to say something about it. And we actually beat Google in the results. where Google are all these blue ones, and Google said this is one of the streets in 9th Street in the Duke campus, and these are the 3 stores, and Google said these are the 3 stores. And they were clearly wrong, and the red push pins are really what Ample predicted, and they are definitely correct, because the movement patterns in these 3 stores are different. Right? And again, we are hoping that these stores would be by design different so that we can exploit that diversity. Okay, good. So thoughts over there, main idea is the surrounding is a fingerprint, effective for separating out nearby context. In reality, spatially clustered shops are diverse by design, and that really aids ample and surround sets. And we are trying to augment that with cameras as well. We're trying to say, hey, suppose you still cannot say where this guy is, how about the camera taking a couple of pictures, and maybe even the camera has a compass which tells you what is the orientation of the camera. And if the camera is pointing upwards, maybe you know it's the picture of the ceiling. If the camera is pointing sideways, maybe you know it's the picture of the walls. And then you use that information with very basic image processing, and you know, hey, this is a place which has green ceiling, must be a Panera Bread or something else. Right? And we're trying to kind of add everything that you can sense in your surrounding, even peer-to-peer. If you know who are the people around you and they are your social network buddies, maybe you're at a restaurant, right? Things like that. And we are trying to essentially sense the ambience in all kinds of ways and localize accordingly. And this has implications in other kinds of research like activity recognition, advertisements, all kinds of stuff. Okay, so finally the third problem is location privacy, and I think I am running out of time, so I'll quickly tell you what the intuition over here is. I have 10-15 minutes? Oh, that's good. Okay. So location information reveals context clearly, and that's one of the key questions people ask me. And then, but there's a thin line between utility and privacy. If I tell you I'm in Seattle, tell me what restaurant I should go to, you as an application, it's hard for you to reply. If I tell you I'm in room number XYZ at Microsoft, research and tell me what I should be doing next, hey, that's a privacy breach. People might hit the panic button, right? So it's kind of a thin line, where is privacy and where is utility, and we are trying to actually address that problem. Now people have looked at this problem in various angles. One is using pseudonyms. So people said, hey, why don't you say you're Jack or John or Susan, right? But then if there are applications which need continuous querying or tracking, pseudonyms is not good enough. So for example, suppose this is my path, my mobility path, and I'm saying, hey, I'm John, then I say I'm Leslie, Jack, Susan, Alex, and then I get to my office and people know where my office is, people will easily know all these pseudonyms correspond to Romit, right? So that doesn't work in a whole class of applications. Okay? People said, well, what you should do is k-anonymity, where you say, suppose this is you draw a box with say 4 other people. This is a bounding box, and to the application you give this box and say, tell me the restaurants in this box. Hey, well, in a sparse region, this is not going to work. Then you have to wait for other people to come into this box before you give it to the application. It doesn't really have the real-time nature of it, right? So we said, well, it's good for certain applications, but maybe not for another class of applications. Okay, but then what was interesting was a recent work by Marco Gruteser in CCS this year, last year, and that the intuition is actually simple. It says, hey, if you can cloak some regions in mobility traces, you can actually give some amount of anonymity. For example, A is moving, B is moving. If I put my hand on top and then you only see who is coming out, you don't know which was A, which was B. And that can be used towards confusing the attacker, because the attacker does not know what happened in this cloaked region. But this still has a problem. The problem is you're implicitly assuming that A and B are intersecting in both space and time. Right? In a sparse region, that may not happen. Right? Also, you have to do this offline. You would not know who all are going to intersect at what point, so you have to get all the traces, figure out where people have intersected, and cloak them. Also, if you had a query in this point, that query is not going to get resolved. Right? So what we are saying is, hey, we want to tackle all these problems. We want it to be real time. We want it to have high quality of localization, which means I don't want to fuzz the location to a big bounding box. I want to exactly have that location. I want entropy guarantees. I want some privacy guarantees from the system, and I want it to work even in a sparse region. Okay, so what we did was what we called cache cloak, and again the intuition is exploit mobility predictions to create confusions. And let me actually jump to the idea. Okay, by the way, the architecture is here. We are proposing a kind of a third-party cache cloak system in which we assume that the users will trust cache cloak, which is a limitation. But assuming users are willing to do that, cache cloak will do some anonymizing and will actually give an API to the location applications, and the location applications won't be able to figure out or track you while you're moving. Okay, so given that, our basic idea is as follows. So let's say, okay, maybe I should just jump to the figure and actually do that. So let's say user A is driving this path and user B is driving this path, right? What cache cloak does is cache cloak knows the individual locations, but cache cloak gives this entire path to the attacker or to the application. So the application's view is this: the entire path of A and the entire path of B. Okay? The application replies to each of these locations. Say the query is, what are the restaurants around this place? So the application replies to that query for every location here and for here. Okay? Now suppose this user has taken a turn and goes to this new path. What cache cloak does is it predicts the user's path and makes sure that that predicted path intersects with some other existing path. So, and then it actually gives this entire set of paths to the application, so the application now sees this. Now observe that the application cannot figure out whether the user turned from here, from here, from here, or from here. So as the users are taking turns, it's more and more difficult to actually track the user. Right? You can actually give privacy guarantees on top of this. If you want to achieve certain guarantees, you can do spurious branching. So for example, you can take a branch out of this and make it connect to this region. So then you do not know whether some guy came from here and came like that, or some guy came from here, or some guy came from here, and so on and so forth. So if you look at it from entropy perspective, at every intersection, the entropy is increasing. Right? Or in other words, the probability that you can track this guy is kind of diffusing with time. And that kind of gives you anonymity to quite a good extent. And the thing to note is, you are getting high quality responses because the application is telling cache cloak what are the restaurants for each of this location. Cache cloak is caching that, and when you get to that point, cache cloak is telling you here are the locations, here are the restaurants for this location. There is a trade-off. It's not all win-win. There's a lot of overhead that comes in because the application is responding to all these locations, right? But then we are saying, or we are thinking that that's on the wired infrastructure. Maybe we can live with that. If that buys us privacy, that's a trade-off we are ready to live with, right? And question?
I'm not sure. It seems like cache cloak knows everything at all times, right?
Yes.
So why is this a solution to privacy?
So we are assuming that cache cloak is trusted. Verizon knows exactly your locations all the time. Right.
They know location within 400 meters. They don't know exactly where I am.
Right.
So, but this will give me the exact location.
I mean, either Verizon knows, and therefore you might as well tell everybody, because federal government can query Verizon and they know where you are at all times, or you don't tell anybody.
But I mean, our take is that if you trust one service, and if that guy knows, yes. I mean, if you do not want to do that, then you have to make this, you have to fuzz that out in some sense. But if you can trust one service, you can do the rest.
I think his point is more that you can't trust. Essentially, if you can trust one service, you're telling everybody, because the U.S. government can always come and subpoena them and later get a law passed in Congress to get them.
Yeah, I mean YouTube, right? I'm sure you heard.
Yes.
So I
Agreed.
think it's a valid comment that you can't trust. You can either trust everybody or nobody.
Agreed. Yes. So that's the limitation of this approach. Yeah. But okay. So anyway, if we go through and we calculated the entropy for each of these locations, and then we see that over time at every intersection, the entropy actually goes down very quickly, and in within around. Okay. So by the way, we simulated this in a simulator, and we took Durham's map, and we used the U.S. Sensor Bureau trace data, which has all kinds of traces for vehicle mobility with the speed limits, traffic lights, etc. And we found out that the entropy actually increases very quickly with time. So within 5 minutes, you can achieve a pretty high amount of entropy, and you can still get accurate, pretty good quality of service in terms of the responses to your query. And again, the overhead is not too much, simply because Cloak can cache these information. And if your query has an expiry time of say 20 minutes, that is huge. I mean, that brings down the overhead a lot. Even with 1 minute, we saw that the overhead is not too much, especially if it's on the wired backbone. Yes, but again, that is definitely true. We do assume that you have this trusted server whom you can trust, and that may not be true, as you pointed it out. Yeah. And again, if you want some amount of privacy guarantees, you can do adaptive branching. You branch anywhere you want, or intelligently, of course. And you can also introduce dummy users into the system, right? And as if there are other users which the attacker doesn't know, but which are actually dummy, and if they can emulate human mobility patterns, you can actually even confuse the attacker even more. Okay, so closing thoughts. Two nodes may intersect in space but not in time, hence mixing is not possible. There's a whole bunch of papers which have actually kind of assumed this model. Our belief is that mobility prediction can actually allow mixing in both space-time, right? Simply because you're predicting. So even if you are not there in this room at the right time, or we are not in this room together, by prediction we might be intersecting in this room at the same space and time, and that is what really underlies Cloak, and that gives you the benefits. Okay, so in conclusion, the Virtual Information Telescope is a generalization of mobile location-based social participatory computing, and this is essentially the vision. You envision every mobile phone as a lens, and you see the world through the eyes and ears of these lenses. Just developing applications is not enough. We believe there's a whole bunch of research challenges that underlie these applications, especially if you want to go past the demo stage. And we've actually been looking at this space of research through the project Microblog and the several projects coming up after that. And the current snapshot of our research are these four projects. The Microblog is the overall system and application. NLOC is energy efficient localization. GPS is too power hungry. You want to optimize that. Surround Sense and Ample is essentially symbolic localization that is aware of your context, sensing everything in your surrounding and trying to say where you are. And Cloak is location privacy via some kind of mobility prediction. So we have a couple of other things that we are kind of emerging in our labs. So for more information, please stay tuned to our lab, which is Systems Networking Research Lab, synergy.ee.duke.edu. And with that, I'll stop here and I'll be glad to take questions. Thanks a lot. Thank you.
About the trusting Cloak, aren't there like plenty precedents for people trusting like their bank or similar things like that? There's a big difference between advertising to everybody what my salary is and my bank knowing it, right? So I would say that, I mean, this model doesn't like seem totally bogus to me. And VeriSign is also like an example of a trusted third party.
Yeah, but there's no precedent on location yet.
Yeah.
Right? There's no precedent that whether people are okay letting other people know their location. In case of banks, so the bank knows what my balance is. Right? They are managing my balance. Nobody's managing my location. I don't know if people are willing to give that.
I think it's just a question really of degree of privacy, right? I mean, G2's point about subpoenas is absolutely valid. If somebody has the information and then there's reason to need to get it, then you can get it through the legal system.
Yeah, but that goes for these other institutions too, right?
Oh, yeah,
Yeah,
except there are well-defined legal protections for the transfer of information, right? That's why there are all these laws about PII
We've
can
just
be
seen
given
that.
out.
We've just seen that the telco, that the legal
Protections
framework for that-
disappear.
Yeah.
Yes.
So
Yeah. So you shouldn't assume that your salary is private then.
Well, I think you can make the argument that your salary isn't private from the US government, so.
Actually, that's true. I
But-
realize
but-
it.
it depends on who you're trying to protect against. There's a big difference between protecting against the government knowing things or just a random person out there writing an application that can figure out my information.
Yeah, but why, I guess the whole, it seems to me the whole point of having this one trusted entity is so that you don't have to trust, your provider, Verizon or whoever, right? I mean, who else is going to know? I mean, who are you protecting it from by having this intermediary? Why would you trust them more than the intermediary? That's what wasn't clear to me.
I was assuming that the applications were not necessarily just written by your provider.
Yeah, the applications could be written by anyone else, like web services or something. And they would like to have your location, but you don't want to trust them, but you want to trust this one entity which builds reputations.
Actually, yeah, the very same model is a good potential. You trust the certificate person.
Right.
So are you requiring that applications have to use this interface? Right.
I mean, we are assuming that someone will buy the interface, someone will buy Cloak and use that interface to get the privacy-aware locations.
So why would applications want to use it? If the application developers or the system
Well,
wants to
it
know.
depends on whether users are willing to go outside. Suppose Cloak is successful, users may not be willing to go to, users may want to get associated to Cloak only, and that user base might be the reason why applications want to tap into that.
Thank you.
Thanks a lot.
Thanks.